Hey Addison, and I didn't have time yesterday to congratulate you. Alison received yesterday an award that is given by the University of Minnesota, and yeah, it went very well. It's the Lawrence Stroff Award.
Thanks, Layla.
Congratulations, Alison.
Thanks, guys. It was one of those Zoom ceremonies that, like normally would have been like a seminar in Minnesota. So it was kind of my first like special Zoom event. I have to say that I'm glad that I guess I would hate to like win something major this year because it's just like all of these Zoom ceremonies, they just fall kind of like flat relative to, to like what you would get in the real experience. But it was very nice.
And what was the award for, other than general awesome?
It was for my PhD dissertation, which is kind of funny because it's 3 years now. So it's actually from last fall, but I couldn't go to Minnesota because I was pregnant, and then the spring the pandemic hit, so it ended up being from our basements.
Nice. I mean,
Okay, Jonathan, I think it's a good time to start.
Which screen am I sharing? Am I sharing the right one?
Yes, you're showing the paper and some notes.
Okay, cool.
Yes.
Just want to make sure. All right, so Mash, did you want to start or do you want me to?
I can get started and then like you can take over.
Okay.
All right. Okay, so this paper is a very interesting one. It sort of connects with my work in a way. When Hoshin shared it with me about a month ago, probably, it really grabbed my attention because like I'm working with networks and modularity is something I'm interested in. Okay, so what this paper does is introduces an information-theoretic approach to network modularity. So this basically lies in the intersection between information theory and modularity. So this paper, in this paper, the authors discuss this network information bottleneck algorithm where they introduce like sort of a hard clustering method to sort of, so if there's an input variable, they sort of like, and it lies somewhere in between, the algorithm sort of pushes it to one module or the other. So it's like a hard clustering method. So that's network information bottleneck algorithm. What this paper also does is it distinguishes between network modularity from partition modularity. And then they test it on different types of modular networks. So they test it on synthetic Monte Carlo, like ERDAS networks. And then they test it on collaboration networks, which is a network of like authors in the American Physical Society. And then they test it on a biological network. So in the results, they discuss about network modularity break-even point, which is a point where, so basically there's a point where one can only gain further simplicity in a network by losing an equivalent amount of fidelity. And that's a normalized simplicity and normalized fidelity. If we can move on to the next slide. Yeah. Okay, so let's quickly go over what information bottleneck means. So we all know we are kind of like familiar with mutual information, which is the information that one variable tells about another variable, basically decreasing entropy, and is represented by the first equation on the right side. And then if you consider clustering, so basically clustering is a compressed description of some data that captures relevant information. So it's if put simply, that's kind of like what clustering does. So let's consider three types of variable. The first being an input random variable. And this is where we are introducing an input random variable into a cluster. And let's consider Y to be a relevance variable. So let's say if the input variable is some sort of let's say a paper, a document with a distribution, or like a set of documents with a distribution, and then you put it into a cluster, and then you have some sort of relevance variables such as a Jensen-Shannon divergence or Kullback-Leibler divergence or something like that. And then like you have a hard cluster assignment variable, which is Z, right? So these are the three types of variables we're considering here. So the information bottleneck, what it does, it outputs a probabilistic cluster assignment function, which is equal to the probability to be in the cluster Z for an input X. And so, yeah, so the information bottleneck provides a constraint, right? And it it doesn't, like whenever there's an in between input variable, it sort of like hard clusters it and like pushes it to one module or the another. Okay, so clustering basically minimizes the mutual information between the input variable and the cluster assignment input variable, while constraining the possible loss of mutual information between the cluster assignment input variable and the relevance variable. So in the ground state, each possible state input variable is assigned with a unit probability to one and only one state of the model cluster assignment input variable. So finding modules within a network is a type of clustering, right? And the correct or the appropriate type of clustering framework is one that sort of preserves the mutual information, or another way to put it is that it preserves the information that is deemed relevant. Okay, so for the next slide, Jonathan will take over.
Okay, the next component to these network modularity measures is diffusive distributions defined over a graph. And this is a joint distribution which shows the probability that a random walk or a diffusive process will land on a particular node given a starting point of that node. So for instance, this is on the right here. This is a graph taken from a dissertation in 2012, but it shows the diffusive process through a random walk where we start on one node and randomly step to other nodes based on a defined prior probability. And the darker the red is, the higher the probability is that we will land on that node given the starting point. Okay, so that's the diffusive distributions over the graph. And then here is kind of, I think this is kind of the crux.
Sorry, Jonathan,
Yeah.
Can I ask a question?
Yes.
So this is just a matter of how many connections there are towards this particular node?
Yeah, that's right. This K value here, sorry, I didn't define all the variables. This K value here does indicate how many connections there are, how many neighbors there are to the node Y, which you're computing this joint probability.
Thanks.
Does that make sense? And so this is the neighbor matrix right here, the weights, given the amount of connections it has. And so to quantify, so we're quantifying network modularity, and I'm going to distinguish between the partition modularity real quick, and then I'll talk about the network modularity, where the partition modularity is concerned mostly with the individual communities of modules. And so this is a way to measure modularity individually throughout the network. But this, this new quantification of modularity attempts to quantify the entire network itself. How modular can the entire network be? So the measure of modularity is the integral under this information curve here. So this is the ratio of information Z and Y to X and Y, and ratio of information z of x over the Shannon entropy of x. And if in a perfectly organized system, we have a network modularity of 1. In a perfectly random system, we have a network modularity of 0.5. And then in 2 of their examples, they have the synthetic example, the Monte Carlo generated Erdos-like system. They're assigning a typical modularity value here. They actually didn't say what it was, but it's under it's well under 1. It's somewhere between 0.5 and 1. And then their network of authorship in the American Physical Society is very close to 1. So this is a very modular system. And then a perfectly random system is the break-even curve at 0.5. But one thing I did not kind of pick up from the paper is what kind of a system would be under 0.5, because this measure goes from 0 to 1, and I can understand how a perfectly random system would have a measure of 0.5. I'm not quite clear on what happens under 0.5. And so this is the measure of network modularity. So then from here, we can go to the results, but we wanted to stop and just see if there's any discussion about these methods.
You know, maybe there cannot be, sorry.
Go ahead, please.
Maybe it's impossible to have systems with values smaller than 0.5, like in a Gini index curve. You also, the best you can have, or the worst, is the first diagonal, but nothing below. But one question I have is, can you draw such a perfectly random system and also perfectly organized? What it would look like?
Oh, can I?
Yes.
I could try and do it on my pen and paper real quick. So I'll draw just two systems. And I don't know if I can conceptually draw a perfectly random and perfectly modular, but I think this will be close. Let's see. So I think that on this would be perfectly random if there's very even space between all nodes in the system, and close to modular if there is definitive communities within the system or the network. Does that kind of make sense?
I think what you're trying to draw here is like a system in equilibrium, sort of like a network in equilibrium. So that would be like a perfectly organized system. And then a perfectly that would be a perfectly random system. The converse would be a perfectly organized system.
Yeah. I'm not sure it would be
is it really possible to achieve like a perfectly organized network? Like in theory, maybe, but in reality, possibly not.
I don't know.
So I have a question.
Okay.
I think I sort of get why this is, but part of the information bottleneck, or part of the goal, is to minimize I, X, and Z, which is like the kind of the X-axis there. And is that just because Z is the number of clusters? So Z is the clustering and X is the input. And basically, is it saying that you want to get the most simple partitioning is why you want to minimize Z, or is there some other reason?
Yeah.
That's what I sort of read it as.
Yeah. The goal of this, like this paper tries to achieve that, right? So it tries to remove the in between element, like in between variables, right? and then like it sort of hard clusters them so that like they belong to either module, like they belong to one module and not the other, right? So that improves the modularity, or improves the partitioning, and thus the modularity of networks. That's my understanding anyways.
I have a question. From reading the paper, I understood that this technique is only useful for undirected networks, or perhaps it also works for directed networks. What do you think?
Well, I don't know how a diffusive distribution over a directed network would look.
Yeah, like for instance, if you have a time series or a set of time series, then I'm not sure if this will apply to that arrangement of the network. Because at the end of the paper, it says that these can work for any network, including those that have weighted edges. But I'm not sure. I didn't understood how the diffusive distribution works for that too.
We're going to, I think next 3 weeks from now, we'll talk about the information bottleneck paper itself. It's possible that some of these questions will become clearer then. Because here's an application of the information bottleneck concept to networks. But in my own mind, sort of problem I have in mind is, let's say we take a watershed system, let's say a groundwater system, well, everything in the subsurface. And we represent it in very fine resolution and detail. And then we ask, how would we group the nodes in that groundwater system into collections so that I could represent things in terms of dominant behaviors like surface water, groundwater, water far from the river, water close to the river, so on and so forth. In other words, to me, this relates a lot to the idea of reduced order modeling, where you're trying to preserve something which you call irrelevant information. And in that sense, it connects very directly to the goal of science, which is to come up with a simplified representation or explanation of something. So that's what attracted me to the thing in the first place. Rather than, so there may be details of how you have to work that out, but as a broad sort of context or concept.
Yeah, one thing I noticed going through the paper and going through some of the citations in the paper was that a lot of people that work on this topic are from dynamic systems science applications of it. And so I didn't spend much time looking at those applications, but I think there's probably a lot of dynamic systems out there that are using this, and that would be a good next place to go, I think.
So maybe, yeah, so maybe that is one way to think of it, is in terms of static networks and dynamic networks, and why this seemed relevant, directly relevant to what Mash was doing was he sort of, I mean, it's a semi-dynamic system that you're dealing with, right, Mash? But you're sort of assuming time slices, and you could take a paper and it might have thousands of words, and you're trying to reduce it to 10 words, which are most relevant to gender diversity, for example, or something, right? You could probably come up with some interesting examples like that of how the concept would be applied as opposed to the actual methodology that's followed in a particular application.
Yeah, if you don't mind, I want to bring up the visualization I have for my research. Can I share my screen?
Just a sec.
Okay, thank you.
Okay.
Yeah. Okay. Okay, can you all see my screen?
Yes.
All right. Okay, so this is sort of the website that I'm building right now. It's based on Flask, which is a framework for building websites using Python. So when all the functionalities are achieved, we'll be able to generate these things. These are called force-directed graphs. And as you can see here, so basically each of these nodes are a paper in hydrology, and you can play around with them, right? And this all these are like these colors, they represent a certain topic, and the connections between them are sort of the relevance between them is established by Jensen-Shannon distance. And so these this sort of measures, these relevance measures are generated from the latent Dirichlet allocation learning algorithm. And so basically what I want to do here is, like, you know, based on your selection, let's say a journal and then year and then some topics, we'll generate, the user will be able to generate force-directed graphs such as this and look at the different papers that are in different topics, and in a sort of like a low dimensional like space, right? And these are force-directed graphs, so these are directed graphs. So I was wondering, like, how I can apply this sort of information bottleneck, network information bottleneck algorithm to a case such as this. Is it actually possible? And I would like to have all of your input on this.
So a question about your color coding. Which color would the paper 23 Unsolved Questions in Hydrology have? Because it covers all the topics that you could possibly find in hydrology.
Mm-hmm. Yeah, that is a good question. So right now, like, we have here this particular graph here is of 25 topics, but we were working on topic refinement and we are up to like 30 topics. So a paper such as that would probably be somewhere, yeah, that is a good question.
Well, your topic model would have assigned it to a certain a topic.
Yeah.
Now, obviously, that brings up maybe a interesting point about your topic model, but all the papers have to be assigned to one topic. Is that correct?
And not really. Basically, what we're achieving here is a document topic distribution. So every paper would like have some assignment, like some other, like the document topic assignment would there would be some degree of document topic assignment to each paper, right? But the maximum likelihood of that document of appearing in a certain topic, that's what this graph demonstrates, or that's what the that's what the LDA churns out, right? So yeah, so we're looking at the maximum likelihood.
So if that 23 questions in hydrology had a uniform distribution,
yeah,
which it probably would.
It was an unfair question. I'm sorry.
No, it's actually a pretty good question. Yeah, Hoshin.
Well, so my question is actually related. It seems like you've got two tasks.
Mm-hmm.
The first task is to choose what are considered relevance variables.
Mm-hmm.
And then the second task is to do the assignment. in such a way that you maximize or preserve the information conveyed in terms of relevance, right?
Yeah.
So the question then becomes is, if you already have an idea of what you want your relevance variables to be, then this paper sort of outlines how you go about doing the calculations, right? The more challenging question perhaps is knowing what the relevance variables ought to be and how many they should be. And in your case with your papers, how did you establish the relevance variables?
So in my case, what we used is Jensen-Shannon distance, which is basically the square root of Jensen-Shannon divergence, and Jensen-Shannon divergence comes from half and half of like Kullback-Leibler divergence.
Yeah, but how did you actually choose the topic headings, what I'm calling the relevance variables, as opposed to doing the clustering? Yeah.
Okay, the topic headings.
Yeah, I mean, you could choose uncertainty, optimization, you know, whatever. These are topics, but these would be ones you have in your head beforehand, as opposed to ones that might emerge naturally from the literature.
Yeah. So basically, the topic headings. Okay. So you know, the latent Dirichlet allocation, what it does is that it basically assigns a document topic distribution, right? And so we can look at the distributions and like, so what is the maximum sort of like likelihood of of a paper appearing in a certain topic, right? And then we can look at the sort of the word document distribution. So what are the most likely words to appear in that document? And then like, so we can look at those words and then we can sort of have like an understanding, sort of have a subjective understanding of what the topic it belongs to. And kind of like when we were naming the topics, like we sent you like the email and you sort of participated in that process, right? By looking at the different words, the most likely words appearing in a certain document, or most likely words appearing in a certain topic. So the document topic distribution and the word topic distributions combined together sort of so directs us towards the sort of like a subjective, objective approach towards like topic assignment. Yes.
So I'm going to argue that when you sent me that list of papers, or sent people that list of papers, they did a relevance assignment which was based on a subjective set of ideas that they had in their heads, right?
Yes.
And was therefore going to be biased strongly by their own personal views as to what would be considered relevant categories, right? And then there'd be some interaction, because you'd look at that and say, well, okay, this doesn't fit into any of my preconceived categories, so let's create a new category or something like that. Yeah. So we as human beings do information bottleneck all the time by taking the data that comes at us and then passing it through some predefined set of relevance variables that we carry around with us, and we somehow update those with time. I'm curious about if you were given just a raw data set and asked to go about doing this, how you would determine, you know, would you need to impose, in other words, does this method require you to pre-impose those relevance variables, or is there some leeway for actually discovering what might be? In this context, I'd just like to point out that it seems to me that in science, as scientists, somewhere in the machine learning literature, I got this impression that there was an approach to machine learning where they're doing feature mapping, and then they wanted the features to be as independent as possible. Right? You take a data set and you identify features and you want them to be as independent as possible. And that made sense to me because I think in science, when we look for features, we also do the same thing. So what we're calling our reduced order explanations of the world are based on identifying features of the world that we think we can manipulate independently.
Yes, Bart.
I have a simpler question actually. Why is this a directed graph? Like what is determining? You said it was a directed graph. What determines the direction in this case?
So basically, this is a force-directed graph, and this is a library in a D3 in JavaScript. So basically, what it does is that it assumes each node has a mass, has a uniform mass of 1, and it it has this force equals to mass into acceleration, and so what it does is that the sort of the relevance sort of measure in between the nodes, it acts as the sort of the acceleration, right? So that's the force like drawing the the nodes like together, or like holding the nodes together, and that's why it's like a force-directed graph. Yeah, it's kind
I
of
see. So the force directed is like one term. It's like
it's a one it's a one term. So it really grabbed my attention because like I'm really interested. So basically what it does is that like it's kind of like mimics Newtonian physics, right? It's not really, but it mimics Newtonian physics. So that was really interesting to me, and that's like, okay, let's do this and see like what it actually like looks like. So that was like one of the motivators behind like choosing this graph.
Thanks.
This is Dipankar. So I'm curious, like when you create a figure like this, so probably you also care for the end result. So your response variable. So let's say in one of those 23 unsolved questions. So if you pick one versus another one, so relative importance of different articles would be different. So do you like care for like how those nodes actually interact? And if you take away like one node, so how your end goal will be impacted?
I see what you're talking about. Okay. So we have to like kind of like draw back to the entire procedure. So this is a class of like natural language processing known as topic modeling. So what topic modeling? Topic modeling at the beginning, we do like different types of word models, right? So what we did here is like we have the entire sort of like data set, and then we converted all of them into words, right? Just word tokens. And then we put all of them into a bag, and this is called a bag of words model, right? And then like, you know, we put it through different data pre-processing routines, and eventually like, you know, like sort of like we have this sort of, but all these words are connected to the documents, and the documents are connected to the topics, and the topics are connected to the words. So basically what it does, what it is, it's like an entire, like the entire data set falls within the domain of the latent duration allocation algorithm. And so if you sort of remove one node or so, the connections between sort of the probabilistic relevance between the other nodes are not affected or so, like, or minimally affected, if I'm putting it correctly. Yeah, kind of sure, but not 100%. But yeah, so if sort of like when we are doing what we're doing here, so you're talking about like taking out different nodes and saying, let's say we want to look at the 100 most cited papers in this entire data set, right? So the probabilistic relevance between the different nodes will still be preserved if we take out the other sort of irrelevant papers in our questions, question. And then like we can have a directed graph or a force directed graph visualization or any other type of visualization that sort of makes sense or like helps our cause. Yeah, I hope that answered.
Yeah, so that makes sense, but I would also ask like, does it care for like hierarchical organization of these nodes? I mean, same way, like going back to the original discussion paper we were talking about in the beginning. Yeah. So how does it actually, preserve? Because if we take example, Hussein said in the subsurface, groundwater system. So processes there like kind of have some sort of domino effect or hierarchical organization. So how we can take this that far to account for those impacts?
Yeah, I'm not really sure about like this question, but I can like think about it and come back to you at a later time if that's
Yeah,
okay.
sure.
Yeah. Okay, so just stop sharing my screen for the time being, and we can get back to the paper, I guess, Jonathan.
Yeah. Okay.
Yeah, I was
So-
actually gonna jump in if I could. Jonathan, could you share your slides again? I just wanted to return to the directional sort of case of this.
All right, sharing my screen. Desktop, share screen. Share. Okay. You want to go back to the idea of a directional graph?
Yeah, just yeah, on here. So it seems like, I mean, it seems like this all math would all still work out. It might just be really hard or intractable, but like,
I think it would just diminish if it was directed, wouldn't it?
sure, but I mean, basically you just have to define a different, instead of having a delta in that sort of Tij equation, you would just have that be your weights, I assume. And then from there, you can go and work this all out, but it probably totally depends on the graph structure itself.
It would converge to some, it would converge some module, I guess.
Not sure I follow that.
Some of these nodes would cluster together into single nodes, correct?
Well,
oh, right.
Or modules that you could then replace by single nodes.
right.
Sure.
Yeah, I guess that's what I was thinking. Yeah.
Yeah, I was more thinking kind of a step back where like when you get this random walk stationary distribution, you would, you know, you would end up with much different things, and then kind of propagating that forward through the rest of it. Yeah, I think you would just end up with a much sort of sparser
or some a convergence of some sort, instead of having like a probability distribution over the nodes. It would, well, I guess it would still be a probability distribution, but some would end up being close to 0 and some would be close to 1, I think. But I didn't actually catch in the paper where it said it wouldn't work with directed graphs. I missed that part. Leela, were you the one that mentioned that?
Yeah, I did. Let me check in the paper and I'll share with you. I think it says that it can work for any network. I think it's in the conclusions. I'm gonna check.
Okay. Let's see if I, no, can't do that.
If I'm not mistaken, the major difference between a directed and a non-directed graph is how the probabilities are calculated. Right?
Let's see.
Just above equation 6, they mentioned that this approach treats directed and undirected graphs identically, but then they don't do much with other than making that statement.
Oh, I see. Okay.
Like right there, yeah.
Okay. Well, I guess I missed that part.
Yeah, I think it was there.
I mean, in the context of a diffusive graph, wouldn't it be true that the probability of remaining within the graph would be stronger than the probability of leaving the graph, a portion, a region of the graph?
Well,
Do you
there,
mean like, oh, sorry, go ahead.
I was just thinking, like, in terms of convergence to a portion of the graph. I guess that if the probabilities converge, if it's extended out in time, is that?
So imagine that we have a set of nodes connected by links, and you do your random walk, and the probability of ending up in any particular node from any other node is more or less the same. So it's uniform, right?
Mm-hmm.
In that case, you would not have the ability to build a reduced order network because you've got no basis for clustering nodes together per se. I mean, you could do anything randomly and it would be okay. So I'm thinking that what makes sense here is that that nodes nodes that would get clustered together would be ones where the probability of leaving that cluster of nodes is relatively small. In other words, you would tend to remain within the node within that cluster more strongly than you would moving to another cluster, and that would distinguish the way that I would identify different clusters in the network.
So is that the same as saying that the modularity would be greater if you had a directed graph? So the M than if you had an undirected graph? Is that?
Well, you could have a directed graph which goes around in a circle, right?
Yeah, so if there was a...
Yeah, but then those things that make up the circle, wouldn't they be one cluster, basically?
Yeah.
So let's say you've got 5 nodes in a circle, each of which makes up a cluster, and that's your reduced graph. But before you reduce it, within each of those circles, you had a bunch of nodes that tended to move more between themselves rather than to the next circle.
But wouldn't that mean that your modularity was greater because you could get rid of all these local nodes? Well, not
Yes.
rid of.
Well,
Yes, exactly.
In terms of network modularity.
Network modularity, yeah. Whereas within each node, the modularity would be low, right?
But what if you have weighted edges? If you have some preferential links that are gonna connect. So is that maybe a way to create new modules?
Well, presumably links or preferential links would tend to be retained rather than removed, right?
Is that what relevance like? You know, I guess I was thinking of relevance as the weight of my links to some extent. It's whatever you decide is the important thing that connects 2 nodes together. So is that related?
Yeah, I was thinking the same because here we were thinking more about the nodes, but then the interactions is given by the links.
So following Allison's question, let's say we had a bunch of nodes and they were connected by both mass transfers and energy transfers. Yeah, I'm trying to just make this easier to think about. And let's say we decided our relevance variables were only energy transfers and we didn't care about mass transfers. Then we would want a reduced order network, or we want a clustering which reflected the dominant energy transfers, ignoring what was happening with mass. Would that make sense, Allison?
Yeah, totally. Yeah, totally. I mean, yeah, that's what I was also thinking was that, you know, something you said earlier, was that relevance is kind of subjective of, you know, what you think is the most important thing that's linking your nodes together. But when I think about, you know, say my networks are time series variables and maybe my links are information measures themselves, you can pick from a bunch of those even and, you know, create a bunch of different types of networks. And in each case, two nodes are linked with different strengths depending on, you know, what measure I chose to link them.
So nodes
And it makes sense that that affects your clustering.
And it seems to me we do this in science all the time, right? We put a filter on the world, and the picture that emerges of that world is very strongly influenced by what we want to focus on and ignoring everything else.
That's absolutely true. And I mean, that's going back to the 23 questions on hydrology.
Mm-hmm.
You know, maybe if the distribution is uniform across maybe, let's say, 23 topics, it's still, there might be some predisposition to place that a weight higher on one topic than another.
So as an example, if I take a high resolution distributed groundwater model and I want to reduce this to a low order, a reduced order model, and all I care about is preserving the stream flow, the information about stream flow in the river,
right?
I might throw away a lot of internal complexity. I mean, that would be the challenge, right? And we tend to do that subjectively right now, but it would be really interesting to have a explicit technique for going from full complexity down to reduced complexity to preserve specifically the information we want to maintain. And then when we want to maintain something else, you know, we'll build a different, completely different reduced order model.
I'm wondering if you have a network and then you have like a small portion of that network and you do the same for both, are gonna create the same modules? What do you think?
I think that the highest measure of partitional modularity is all the communities are equal. So it tends to 1 minus 1 over, so in partition modularity, Q tends to 1 minus 1 over Z for a perfectly modular network with Z equally sized modules. Is that what you're?
What I was thinking is that if you do this analysis for a big network and then you recognize what are the modules that are relevant, right? That compile the most important information, but then you go and extract just a small portion of the original network and repeat this process. Would you have the same, like retaining kind of the same properties of the original network, but with a smaller sample? Will it show the same behavior, or? Because that's usually what we do. Like, we cannot collect all the data that we want, that it will be our super big network, but then we end up with a small portion of what is the whole. And so, yeah, I don't know. I was just wondering about that.
That seems to suggest a kind of fractal property, which may or may not be true, right? The question I have for you, Jonathan and Mash, is in network modularity, I start with X. I'm trying to arrive at Z in such a way that I preserve the relevance variable Y and maximize information about Y. Yeah. in the partition approach, what's the guiding principle? The analogous guiding principle?
Well, I wasn't thinking too much about the partition approach because it set up the partition approach like kind of the non-information preserving approach, and which is why they introduced the network approach. But if we thought about it, we could probably attempt to address that.
Yeah, so the criteria is something else. It's something about geometry or something, but it's not necessarily about any particular thing that I care about more. Well, it could be, I guess geometry could be what I care about. But.
Yeah. Mm-hmm.
When I read the original paper, I was relating this to, you start with a data set in deep learning and you reduce it to a set of features, right? And then you use the features to predict the thing of interest. And so it sounded like there was some analogy going on here where the features were something related to Y, except that in classical unregularized machine learning, the features that you pull out would be whatever the machine learning algorithm happens to focus on. Whereas if you wanted your features to have meaning, interpretability, or something, you would then start to put in regularizing conditions which would guide how those features were selected in some sense. So it sounded to me like there was a very strong relevance of this to the whole issue of interpretability of systems and feature learning.
So in that case, well, or would you say in that case the features are the relevance features?
Could be. I mean, they're relevant in some sense. In machine learning, they're relevant in the sense that identifying those features makes it possible to predict the output, whatever that is, a classification or a regression job, right? But they could be black box in the sense that they have no meaning to you or me.
Right. And in that case, yeah. So it sounds like in that case, we're going from X to Z.
Through Y in that case, yeah.
Through Y in that case. So does Y really matter in that case?
To scientists, it seems to. To engineers, maybe not.
Yeah.
So I think like you ideally want something that is like a subjective objective thing, like approach, right? A hybrid approach. Hey, as a scientist / an engineer, like if you want to lie somewhere in the middle, so ideally you want the relevance variable, the information from the relevance variable, as well as the cluster assignment variable, both of them, right? So in our case, like when sort of we are using the relevance variable as a guide to our like subjectivity, and then we are also using the cluster assignment variable to assign a certain topic to a document or something like that. So so in my case, I would depend on both. I would lie somewhere in the middle.
maybe I mischaracterized things a little bit earlier. Z is the output, right? That's the reduced order model. It's the reduced representation of X. It's the clusters.
Yeah.
Whereas Y is something that about which I want to preserve information. I think I stated this the other way before. And so Y would be, in my case, stream flow. I want to preserve information about stream flow. And Z would be the state variables in the dynamical system that I want to cluster all of my observations into somehow, or something like that. My high order state variable I want to reduce to a reduced order state variable. So X is my high order state variable, Z is my reduced order state variable. And the information I want to preserve is the information in Z about Y to be as close as possible to the information in X about Y.
That sounds very much like the LSTM work that Gray and Freddie Kratzert are doing. The cell states themselves have information that we're very much interested in.
The question is how few can we get away with?
Yeah. Right. And if there's too many, detriment the system. Is there an optimum number of hidden states or that preserve the information you want in the structure that you want it?
So I'm trying to relate this to Allison's and Praveen's and problem where you've got a whole bunch of hydrometeorological variables interacting with each other in some kind of a network. And you now want to build a conceptual diagram where you can explain it just using 4 or 5 nodes or something like that. But you need to do it in such a way that you preserve something which you have to determine or you have to impose from outside. In your case, what would that be?
Right. Well, I tried to do it, so I did some network clustering of, say I had like 20 variables from a flux tower, and I had all their mutual informations and transfer entropies and unique information and synergistic information. So I did I think I used like k-nearest neighbors type clustering and, tried to group the variables and kind of see things like, sometimes soil variables would clump together or, variables related to humidity or something would cluster together. But I never went beyond that in terms of like, what do those clusters really mean, or are they persistent across cases? But yeah, and then my other question is like, well, what's the most relevant variable with which to cluster them in the first place? And so I kind of went in a lot of circles there.
An analogous problem I can think of is the one Yuan is working on, where he's trying to build snow schemes, snow fraction to snow water equivalent relationships. And one of the hypotheses is that you would break up the country into regions. So you could build a simplified model in each region, right? So the question then would be, how would you determine those regions so as to lose the minimum amount of information when you did the mapping?
It sounds like the modifiable aerial unit map problem, which is no real good solutions.
I think that provides motivation though for some of the things that I was doing, because I couldn't really say why I was doing them, and then I stopped. But maybe it's that simplification into a reduced order complexity sort of representation of the system.
I think historically science has been very motivated by the simplest representation that maintains the information you're trying to convey. I think.
And in that context, independence, relative statistical independence seems very important, right? Because if every time I change the letter A, I had to change the letter B, then it wouldn't be very useful to me. I should be able to modify A and B relatively independently. Or in grammar, I should be able to, there's some structure, but which conveys meaning, but I should be able to modify the words relatively independently. Otherwise, they wouldn't be that useful to me.
I'm curious. So for this null hypothesis, like you want to break up the entire nation into different regions. So how about like if you did with the response variable, like let's say snow depth or something. So why would that not work?
I'm sure you could have lots of different hypotheses.
Yeah.
The classic one that Yuan is using is just use the regions that have been identified by people beforehand, right?
Oh yeah. Okay. Yeah.
But let's say I gave you the conus and I said, I don't want to treat each pixel independently. I want to cluster them into pixels so that I can reduce the number of models I have to build. If my focus was snow water equivalent, I might use one set of clustering rules. And if my focus was streamflow, I might use a different set of rules. If I was evaporation or vegetation, I might use, in other words, my regions wouldn't necessarily be the same optimally from an information preserving point of view. But very often we just adopt something that somebody else has already subjectively determined is a useful way to think of things.
Yeah, that makes sense.
And that kind of fits exactly why it'd be, I'm not sure it'd be possible to find the network modularity of one, because there's always going to be like one reason to cluster it one way, one reason to cluster it another way. And if you just use every grid pixel across CONUS, then it seems like that would be the network modularity of 0.5.
Close, yeah.
Well, it's 2:09.
Wow, time flies. That's true.
I just wanted to make one final comment. I just want to point out that what Jonathan said alerted me to the fact that pruning links and grouping together aren't necessarily the same thing. So, right, reducing connectivity and clustering together into one group are not necessarily the same problem. They seem to be related, but aren't. Yeah.
So like you can cluster a snow water equivalent group, but you might prune the links of a streamflow group.
Well, thanks. This was very interesting.
Yeah, I have one a question. So like these are like really interesting discussions. Like, and I'm a big fan of science communication. So what do you all think about like like having these discussions up like somewhere where like people can access and like listen to them and something like that? It'd be great to have like, let's say, a YouTube channel or something like that where we can upload these discussions. I'm sure like a lot of people would be interested in like in something like this. Yeah, I'm just like peddling the thought.
Yeah, that's awesome actually. Yeah, I have the videos recorded, so if you wanna give me a hand and help
sure.
me create the YouTube channel.
Definitely.
Yeah,
So we can have so.
Okay, thank you everyone. And we're leaving not before saying thank you to Jonathan and Mashrekur for this awesome organization and for the slides. If you want to share the slides, we have a space in our drive.
Yeah, I'll upload them to there.
Awesome. Okay,
It's great to see you all.
Yeah.
Yeah.
All right.
Thanks, guys. See you
Take
later.
care, everybody. Thank you.
Bye bye. Take care.
Stay safe.